Hello dear students, uh, welcome to the video lecture of design and analysis of algorithm. So today in this video lecture we are going to solve another recursive algorithm, that is finding the number of bits to represent a decimal number. So here a decimal number is converted into binary format, and in the binary format we are counting the number of bits which are present in that binary number. So already we have seen this example in a non-recursive algorithm, analysis of non-recursive algorithm. But here this algorithm is recursive algorithm. So the algorithm name which I have given is bit count of n, where n is the input non-negative integer, that is n. Input is non-negative integer. Output, you have to count the number of bits required, or you have to add up the number of bits which are present in that binary number. So the algorithm or basic operation of the algorithm goes like this: if n is equal to or less than or equal to 1, then it will return 1. So now there is no counting operation takes place when n equal to 1. So you can set up the initial condition for this algorithm, that is when n equal to 1. So there is no counting operation takes place because it is returning one value. So hence the basic relation or basic operation, it depends on only this stuff, that is it will if n is greater than 1, then it will return 1 plus bit count of floor value of n by 2. So as you can see, this is the recursive function here. So bit count of n by 2, each time it will take the number, it will divide that number by 2, and we have to take its floor value of that number. So this is the algorithm or recursive algorithm to count the number of bits present in the decimal. So now we have to do the mathematical analysis of this algorithm. So as you know, we have to follow 5 steps here. So first step, we have to decide the number of input parameter. The input parameter, as you already know, it is n. So this is very, very important, that is you have to decide the basic operation, or you have to find the basic operation. So here the basic operation is addition. So please remember that most of you are thinking that this n by 2 will take maximum time, so division is a basic operation. No, because this problem definition itself indicates we have to count the number of bits. So for counting the number of bits, so the basic operation becomes count, that is addition of that particular bits. That becomes a basic operation. So don't get confused here, because the aim itself, they are giving that we have to count the number of bits which are present in that binary number. So addition becomes a basic operation here, not the division. Please note this point carefully. So next is the third step, that is whether we are doing it for best case, average case, and worst case. No, because it only depends on the value of n. So next step, in the fourth step, we have to set up the recurrence relation for this algorithm. So as you know that in this algorithm, as we have already studied, it will return 1 when n is equal to or less than 1, and otherwise it will return 1 plus bit count of n by 2. So please observe where whenever n equal to 1, it is not doing any counting operation. So we can perform our initial condition as whenever n equal to less than 1, so it is 0. So this is our basic operation, because when n value is less than or equal to 1, we are not doing any counting operation. So the basic relation or basic operation becomes initial condition becomes 0. So otherwise it is doing 1 plus a of n by 2. So floor value of that n by 2 whenever n greater than. So this is our recurrence relation for this algorithm. So let us solve this or simplify this algorithm. So as you know, to solve this recurrence relation, we have to apply the backward substitution method. So as you know, n this initial condition. So when a of n value is equal to 1, so it is 0. Whenever n equal to 1 or less than 1, so initial the condition is 0, because we are not doing any counting operation. So further we will simplify it, where a plus n by 2, I can write it as 1 plus a of n by 4. Again, if we can substitute this value, so it is 1 plus 1 plus 1, a of n by 8. Again it becomes 1 plus 1 plus 1 plus 1, a of n by 16, like this. So it becomes very, very complicated if we do like this. Because of this complication in the solving of this reconciliation, what we can do is we can apply one more method here, which is called as the substitution method, where I can use n value is equal to 2 raised to k. So this method is called as substitution method. So this is because we are substituting this n value equal to 2 raised to k, because if we solve like this, it becomes very complicated. So let us substitute n equal to k and let us check what is that what we can do. So here we have applied 1 plus a of 2 raised to k by 2. As you know, this is n value, we have substituted it as 2 raised to k. So it becomes 2 raised to k by 2. So 2 raised to k by 2, according to the rule, it becomes 2 raised to k minus 1, a of 2 raised to k minus 1. So now we can further simplify very easily. Next step, for this we will again apply the substitution method. So it becomes 1 plus 1 plus a of 2 raised to k minus 2. So 1 plus 1 is equal to 2. So plus a raised to a of 2 raised to k minus 2. So like this, now we are finding one pattern here. So 3 plus a raised to a of 2 raised to k minus 3. Next 4 plus a of 2 raised to k minus 4. Like this, it goes on up to the k. So last it becomes k plus a raised to k minus k. So what is k minus k? It is nothing but 0. 2 raised to 0 is nothing but 1. And we already know that a of 1 is nothing but 0, as we know the initial condition a of 1 is nothing but 0. So we can substitute this value. So this whole term becomes 0 and remaining term here is k. So the equation is easily solved now. So it is a of n equal to k. So we already know that n value we have substituted as 2 raised to k. Now we have to find what is this k. So to find what is this k, we can apply log to the base 2. So on applying log to the base 2 for this equation, so this equation becomes log to the base 2 of n equal to k into log to the base 2 of 2. So you know that log to the base 2 of 2 is 1. So we can solve it for k now. So k equal to log to the base 2 of n. So you already know what is k. K is nothing but a of n. So it is log to the base 2 of n. And we can solve this, or we can rewrite this equation as a of n belongs to theta of log to the base 2 of n. So this is the order of growth, which is the logarithmic order of growth of this algorithm. So please be careful while solving this algorithm, because most of you get confused at this basic operation. So here the basic operation is counting, and don't confuse that the basic operation is dividing here, because we have, in the aim of this algorithm, he has clearly mentioned that we have to count the number of bits present in that binary number. So if you have any doubts, you can ask through the WhatsApp, or you can ask